Hello, everyone, and welcome back to the FY 2023 CINR webinar. Now we're going to proceed with topic area 7, which is advanced nuclear materials. And our first presenter is Sue Lesica for NM1 light water reactor core or structural materials. Go ahead, Sue.
Thank you. I'm Sue Lesica, and first I'll begin with an overview for this topical area, advanced nuclear materials. Obviously, we save the very best for last on this webinar, materials. So first I will begin with an overview for this topic. That's particularly important this year as you may have seen, we have changed the structure of the plan solicitation. And so there will be a topic at the end, NM5, for other advanced nuclear materials topics. And this will be in addition to the more specific topics that we'll be talking about prior to for NM1 through 4. And NM5 has a much more open is a much more open topic, and so the overview is particularly important to give you an idea of what we envision falling under NM5. So let's begin with the overview. Please, next slide. So topic area 7, advanced nuclear materials. The topic areas in this topic area, we invite applications that cover key material science topics to better understand some of our knowledge gaps in different areas for materials. First, core and structural materials. I will be talking about one specific area under core and structural materials, but again, if you have some interest in that area, that is outside of my specific scope that I'm going to talk to you about in NM1, I refer you to the other category. The next topic is advanced materials manufacturing techniques. We have a specific scope in that area as well that you'll be hearing about. Then qualifications and testing of existing materials. Also developing new classes of materials for nuclear reactors. So this is more of a materials discovery topic. Materials for advanced fuel recycle. I want to emphasize here the materials portion of this topic. Fuels is covered under a separate topic. So this would be more the materials that are used to facilitate fuel recycle, but not the fuel itself. Fuel itself is in that separate topic. Also included under this topic area are environmental effects, thermal effects, irradiation effects, all of those different conditions that a material might see and have to withstand during the operation of a nuclear fission reactor. And then there's the last bullet is other relevant areas, including materials to mobilize fission products and off-gas capture species. There will be a specific topic discussed by Kimberly Gray coming up, but that is also an area of interest and part of the NE mission. Next slide, please. So the first topical area is focused on light water reactors. Part of the NE mission is to support and facilitate our current fleet of reactors, and that is the goal of this topic, of this subtopic in particular. So the focus here is light water reactors, and is to understand environmentally assisted fatigue, which is a damage mechanism that may limit the extended operation of light water reactors. So it's an area that particularly is of interest and must be understood in order for us to continue to support the current reactor fleet. So there are test programs in the US and abroad that have shown that the water environment in an LWR reduces the fatigue life of light water reactor structural materials compared to their expected life in air. And so what this topic is focused on is to better understand why that is and what the loading conditions are for these materials. The application, the proposal should also include studying the damage mechanisms to have a better fundamental understanding of what is going on in the structural materials in the LWR, and what are the effects of the different loading conditions, material variabilities, and the different water environments. And this could be done via experimental testing, characterization, modeling, and of course a combination of the two. And once again, the goal is to address the uncertainty and the conservatism that's in the current environmentally assisted fatigue prediction that has been developed to support the long-term operation of the LWR reactor fleet. Should we continue on, or should we take questions for this topic now? Okay,
Hi,
I will
Sue.
continue on.
Sorry about that. Please keep going. And at the very end of all the presentations for topic area 7, we will do the Q&A. So thank you for asking.
Okay, great. Okay, ongoing work that's relevant to this subtopic area. Under the Light Water Reactor Sustainability Program, which is an ongoing program within NE, there is a materials research pathway, and we have ongoing research in many areas related to materials degradation. And this slide lists some of the areas that may be of interest, characterizing and understanding low alloy steels, stainless steels, their weldments, understanding those materials' cyclic behavior, also developing temperature and stress analysis, and particularly during light water reactor baseline and transient conditions. We have an excellent website that's listed there on the slide that you can get more information and prior reports for work in this area. That's probably the most direct place to go. OSTI also has an excellent website that has a catalog of our reports. Next slide, please. So areas not of interest. So we need to focus on the NE mission, the nuclear energy mission. So our focus is on fission reactors, the current fleet of reactors. So anything outside of that would not be considered relevant. So fusion reactors are not relevant. Advanced reactors is not relevant for this particular piece of this particular scope. Non-proliferation issues, weapons R&D, isotope production, and nuclear medicine related technologies are all outside of the scope of this subtopic. Next slide, please. I will start our description of the next subtopic, and the goal for this subtopic is to ensure a pipeline of qualified core and structural materials for advanced reactors so that they can be deployed economically and efficiently to support the DOE's decarbonization goal. So the specific technical issue, the knowledge gap that we're trying to address in this subtopic is that there is some mechanistic understanding of creep damage and fatigue damage under elevated temperature service. However, what has been observed is that once these two mechanisms are combined, it significantly reduces the cyclic life of the structural components. And how those two, creep and fatigue, interact is not well understood. And so that's what we're trying to, that's the goal of this subtopic, is to better understand creep damage, fatigue damage, and the interaction of the two, with the goal of being able to more accurately predict the behavior of the structural materials under those conditions. And not only will this support understanding the existing materials, once we understand the mechanisms and how they interact, that can be used to develop new materials that are more resistant to creep fatigue failure. The last bullet there defines the material systems of interest: austenitic steels, ferritic, martensitic steels, and nickel-based alloys. You don't have to cover all of these different material systems. You can choose one. I do ask, though, that you make it quite clear in your proposal what material system you're choosing, so that we can, so it's quite clear on what your goals are and what you'll be looking at. Next slide, please. Ongoing work relevant to this subtopic area. There's quite a bit of research on elevated temperature mechanical properties for alloy 617, 709, and optimized grade 92. These could be found on OSFI for the federally funded materials research. There's other sources within the literature that you can find that could give you a start on what the current state of the art is in this area. Next slide, please. So as I said, the material systems that we're looking at are rather particular. The areas that are not relevant are nuclear graphite, which has its own creep issues, composite materials, and refractory metals. If you have interest in these material systems, you could take a look at the other category and propose there. It would not be appropriate or relevant to propose for these material systems in NM2. Next slide, please. This next slide is for our next topic, NM3, which I believe, will you be presenting this one?
Yes. Okay.
Thank you.
So thank you. My name is Mei Li. I am the National Technical Director for the Advanced Material and Manufacturing Technology AMMT program. For this subtopic, NM3, Advanced Manufacturing Technology, the federal contact is Dirk Karen Gallimore. He is out of office this week. I'm presenting this subtopic on his behalf. So this subtopic is interesting ideas that can transform materials processing and fabrication techniques to significantly change the cost curve of manufacturing for nuclear energy applications. Area of interest include, but not limited to, the cutting-edge technology of processing and fabrication of composite, concrete, and metals, joining and repair technology, also emerging capabilities developed within the advanced manufacturing enterprise for components, subsystems, systems, and also structure, As you can see, the scope is very broad, and it is intentionally broad to target innovative solutions. Next slide, please. DOE-NE supports a wide range of research that is relevant to this subtopic. One primary program in this area is Advanced Materials and Manufacturing Technology AMMT program. The AMMT program is to develop cross-cutting technologies in support of a broad range of nuclear reactor technologies. Its vision is to accelerate the development, qualification, demonstration, and deployment of advanced materials and manufacturing technology to enable reliable and economical nuclear energy. AMMT program has 3 elements. First is development, qualification, and demonstration. This program element focus on develop advanced materials and manufacturing technology, establish a rapid qualification framework, evaluate material performance in nuclear reactor environments, and to demonstrate new materials and manufacturing technologies in an efficient manner. A second element is capability development and transformative research. This area focuses on developing capabilities needed to support the material development and qualification through advanced characterization tools, high throughput and accelerated testing technique, modeling and simulation, machine learning, and artificial intelligence, and to perform transformative research to develop new material concept and design. The third element is collaborative research and development to focus on collaboration and partnership to support the nuclear energy community needs with a broad set of options. AMMT program has 3 core technical areas: material development, advanced manufacturing, and environmental effect. These 3 technical areas are integrated to support the development, qualification, and demonstration of advanced material manufacturing technology. I should mention that AMMT combines 3 previous programs. One is Advanced Methods for Manufacturing, AMM. The other one is Transformative Challenge Reactor, TCR. The third one is Nuclear Material Discovery and Qualification Initiative, NMDQI. There are other ongoing research activities through other funding mechanisms, including directed research, NUP, SBIR, STTR, and industry FOA. Below are several web links, include the recent AMMT program review meeting, and also NUP, SBIR, and industry FOA award. You can find information about the previous and ongoing research under different programs. Particularly when you look at the NUP award, make sure you check all 3 previous programs, and to identify the research that is not duplicative of our previous or ongoing research. Next slide, please. Area not of interest. Like all other topical area, application need to focus on research that support the DOE-NE mission. Application are not considered relevant to this topic, including nuclear non-proliferation purpose, nuclear weapon R&D, and nuclear medical isotope production, and also nuclear medicine-related technologies. But if application on technology that cross-cut those areas that may be considered responsive, if the proposal can clearly demonstrate the application to nuclear energy. So this is my last slide. I will be available to answer questions at the end of the presentation. Thanks.
Thank you very much, Maymay. Next, we go to NM4, Material for Fuel Recycling Applications with Kimberly Gray. Kimberly, please go ahead when you're ready.
Okay. Good afternoon, everyone. My name is, can you hear me? Hello?
Yes, we can hear you just fine. Thank you.
Okay, I'm sorry. Okay, my name is Kimberly Gray. I am the Federal Program Manager for the Off-Gas Capture and Wasteform Development Area within the Material Recovery and Wasteform Development Program. John Viana from the Pacific Northwest National Laboratory is the technical point of contact for this work. Okay, here's the overview. And we are specifically looking for sorbent materials for off-gas capture. Iodine capture technologies have been used in various used nuclear treatment facilities worldwide, and experimental techniques to separate krypton from used nuclear fuel dissolution gas streams have been treated. Here I give just some general capture media criteria for the applicants to consider. Absorption rates, capture efficiency, loading capacity, and the ability for the conversion of final waste form for long-term disposal. These criteria can be used to assess technologies relating to xenon-krypton separation and iodine capture from off-gas streams arising from used fuel treatment activities. Next slide, please. The Material Recovery and Wasteform Development Campaign has ongoing research through many avenues of funding, including many NEAP projects with various universities partnering with the national laboratories. Please visit the NEAP website for past NEAP projects. Various types of absorbent material for capturing iodine have been studied and developed over the years. Natural or artificial porous materials like zeolites, morganite, alumina, and silica gels have been loaded with various metals such as silver, cadmium, copper, and lead. Other materials such as metal organic frameworks or MOFs materials have been studied for gas separation applications. I've listed a couple of journal articles and milestone reports of previous and ongoing sorbent material developments within our campaign for your review. Next slide, please. For the non-relevant work, the application should focus on research that supports the DOE NE mission. The applications on sorbent material crosscut technologies could be considered responsive if the proposals clearly demonstrate the application to nuclear energy. We would like the applicants to submit proposals with novel approaches that are innovative and out of the box for these sorbent material technologies. The baseline and the most mature technologies for noble gas capture is the cryogenic methods. And the baseline for iodine capture is the silver morganite technology. I encourage you to review the suggested journal articles and the milestone reports and send us any questions that you may have. Good luck, and we look forward to reviewing your proposals. That's all I have. Thank you. And here's our contact information. Feel free to ask questions at the end, or you can always send us emails with your questions. Thank you very much.
Thank you, Kimberly. Now we'll move on to NM5, Other Advanced Nuclear Material Topics with Sue Lessica.
As I mentioned in the overview, the focus of the overview was to give you an idea of what areas are of interest for NM5. There is a focus on what our strategic goals are, which are listed here, enabling the continued operation of the existing reactors, enabling deployment of advanced reactors, developing advanced fuel cycle, and maintaining the U.S. leadership in nuclear energy. And since this topic area is focused on materials, this other category is focused on meeting those goals through materials R&D. For more information, you could take a look at our website. It talks more detail about our programs and the goals, the material goals across the programs. And that's all I have for this slide.
Thank you, Sue, and all of the presenters for topic area 7. So at this point, we will begin with a question and answer portion. So if anybody has questions, please go ahead and type those into the control panel under the question section. And we do have a number of questions that are already here and a few more that are still coming in. So I will begin addressing questions first for NM1. And the first question for that area is if radiation damage would be considered as part of the environment that assists fatigue.
I'm sorry, you broke up, so we kind of missed the beginning of the question.
Oh, okay. Can you hear me all right now?
Yes.
For NM1, will radiation damage be considered as part of the environment that assists fatigue?
I believe we have Frank's on the line if you wanted to take that question.
Sure. So this is Frank. Can everybody hear me?
Yes.
Hear you, Frank.
Okay. For this topic, environmental assisted fatigue, I think traditionally speaking, radiation is not considered.
Okay, thank you for that, Frank.
Yep.
The next question, what are the specific material types that would be relevant for work scope NM1?
This would be the low alloy steels, the stainless steels, and their weldments. Since the reactors are not all the same, there is some variety in the materials. And so that's why we did not particularly specify an alloy. Frank, did you want to add anything to that?
No, Sue, I think you addressed that question very well. I do not have anything to add.
Okay, for the same work scope, NM1, is fatigue or freeting phenomenon of zirconium cladding relevant?
No, that would be under, that's more of a fuels issue. So this would be not within the core.
And I concur with that.
Okay, thank you both. Okay, there are a number of questions. I'm trying to pick out the NM1s first. The next question is relevant to both NM1 and NM2. Do these work scopes seek computational projects or experimental projects?
Most likely what we usually see is a combination of the two. We are not prescribing one way or the other, but in general, we do usually see a mixture of the two. However, we are not prescribing one way or the other.
That's great. And then the follow-up to that question is for proposals focused more on the computational side, can they integrate advanced predictive machine learning methods for prediction purposes? Would that be acceptable or relevant?
Certainly, whatever you have at your disposal to answer the question and increase the knowledge of these issues, these material issues, would be excellent.
Okay, thank you. Okay, this is for NM1, and it's probably similar to a previous question. Yeah, is there any interest in environmentally assisted fatigue or prior irradiated materials?
I'm sorry, you broke up right at the start again. Can you read that again?
One moment, we'll pull that question back up again.
Sue,
Okay.
here it is. Similar to the this may be similar to a previous question, but is there interest in environmentally assisted fatigue of prior irradiated materials?
Frank, you want to take that one?
Sure. For this particular subtopic, NM1, where we are, the focus of the call is addressing the uncertainty as well as over estimation of the current UREC CR 6909, as well as the ASME Section 3 subdivision MB. We are not particularly focusing on the irradiation effect.
Thank you for that. The next question applies to both NM1 and NM2, and the question is if environmental exposure and testing, as well as design for property improvement of relevant structural materials, if they're of interest or relevant to that work scope.
I think for both topics, the information that we gather, and the better we understand these materials, the better that we could use them towards materials discovery, and design. However, that is not the focus for material discovery. Is not the focus for NM1 or NM2. Although the information could eventually be used for that.
Okay.
Did I answer the question?
Well,
so I can speak to NM2, the same sham. In terms of NM2, that we're interested in essentially the creep damage mechanisms, the fatigue damage mechanisms, and their interaction. And creep fatigue interaction damage mechanisms is one of the key. Currently, that our state of knowledge is that we essentially sort of determines the performance of a existing material or try to design new alloys by brute force mechanical property testing. And because that there's no sort of understanding in terms of what is the underlying mechanisms that alloy developers can exploit in order to develop the materials that will have a balanced property. So we are sort of looking for sort of innovations and help in terms of that particular area so that we really can improve our efficiency in terms of establishing this pipeline of qualified materials. Right now, that the current approach of just by brute force testing is very resource and time intensive. So, but creep fatigue is a very difficult sort of phenomena that is both at the local microstructural level as well as in the sort of the structural level as well. So the difference of length scales in terms of the way that the fatigue damage are initiated from the surface, and some of those cavitations and creep damage occurring inside the sort of the structural materials. That the interaction of the two is what sort of cause us structural failure issues. So that's all I have.
Sam, I appreciate that. The next question is for NM1 and NM2, And the question is if the discovery of new structural materials that focus on the characterization of microstructure and thermal properties at elevated temperatures, if that topic falls within the NM1 and or NM2 work scopes.
I can speak on NM2. It's a little bit outside because that I think that, well, if we have a structural materials that indeed that will perform as what we would like to have for high temperature reactors subjected to all these thermal transients that we see in the high temperature reactors, they'll be great. But obviously that we really would like to have the understanding of the mechanism so that we can take advantage and leverage those information so that we don't have to go about to do this sort of time consuming and sort of resource intensive mechanical property testing. So if whatever that is proposed that can address that, I think that for NM2, it will be within the scope, but we would like to sort of be able to apply that for not just one single material, but really for the entire material class so that we can leverage that in addressing the pipeline of materials. We would like to have as many qualified materials as we can so that the advanced reactor designers can take advantage of those wider design windows. Right now that they are really limited by the number of available qualified materials so that sometimes that it really constrain their reactor design. Thank you.
And for NM1, if I want to give an input here, is the call is to address the LWR, the structural materials for the current LWR fleet. So the materials aiming for higher temperature application as well as the associated damage, microstructure mechanism, etc., does not fall into the core of this topic. And also, I want to emphasize that this topic actually has a long history. The very first fatigue testing is started in the 1960s. So there is a lot of results data found in this area. But as we are aiming for operating reactors in longer terms, there are some new issues that we need to address. So that's the key focus of this call.
Thank you both for addressing those for both NM1 and NM2. For both of those work scopes, again, NM1 and NM2, is non-destructive detection of fatigue and creep damage relevant to either of these work scopes?
For NM2, I would imagine that that is as one of the suite of characterization tools that will help us to understand the underlying mechanisms. I think that that will be sort of to that extent for NM2.
For the NM1 side, I think I concur with what Sam just said. The non-destructive elevation is one type of characterization tool. If it can reveal the insight between the actual environmental assisted fatigue damage and addressing the current uncertainty and overestimation of the existing models, that should not be excluded in the proposal. But if you're proposing that technique, you need to provide a convincing case.
Okay, thank you both for that discussion. The next few questions are focused specifically on NM2. The first of those questions is if materials for fusion reactors are considered relevant to NM2.
Yeah, since fusion is outside of the nuclear energy mission, fusion materials materials that are exclusively for fusion are excluded. There is some overlap in the interest in materials between the fusion program and the fission program, which is what this work scope is focused on, but for materials only for fusion, that's outside of the scope.
Yeah, I would like to expand on what Sue said, because the way that the fission reactors, the structural materials that is used in the fission reactors, that the type of thermal loading, transients, etc., are very different than the fusion reactors. So therefore that yes, 316 might be used by both reactor types, but then our requirements will be a little bit different.
Thank you. In the slide for ongoing work that is relevant to work scope NM2, alloy 617, alloy 709, and grade 92 are listed. Does that mean that those alloys are preferred because they complement ongoing work? Or is it better to avoid these alloys to avoid being redundant?
I think that in terms of one of the slides that Sue presented, we emphasize the following, that the material classes, so we sort of highlight the stainless steels, the subnickel alloys, as well as the ferritic martensitic steels that are sort of applicable for different types of structural components for fission reactors. Now, out of that, we are saying that we can only assess all these existing materials or new materials in terms of this fatigue damage failure mode by brute force mechanical property testing. And we would like to get help for the community to sort of look at that from a more fundamental aspects to understand the mechanisms. And that we hope that it can help us to not having to go through if there's any other nickel-based alloys that we would like to use it, but in order to understand whether it can sort of sustain the type of quick fatigue loading for fission reactors, for high temperature reactors. Currently, we can only do mechanical property testing, do a lot of quick fatigue testing. But the scope of this NM2 is to look at the more fundamentals and avoid the mechanical property testing. So if one wants to sort of study alloy 617 as a surrogate to understand all these underlying creep mechanisms, fatigue damage mechanisms, and creep fatigue interactions, that will be okay. There's no overlap in the sense that, as far as the base program is concerned, that these fundamental studies on the mechanisms are not, we don't have it. So there won't be overlap in terms of studying those mechanisms that will sort of allow us to generalize that to the entire nickel-based class, hopefully, or the stainless steels, or the ferritic martensitic steel. Okay.
Sam, thank you. The next question for NM2, do the structural materials spectrum also cover cladding material and accident tolerant fuel clad options?
No.
Yes.
They are
The
structural
cladding is
cladding, but not for fuel cladding. So my distinction on structural cladding is that drawing an analogy to light water reactor fleet, the lower alloy pressure vessel steel will be cladded structurally by stainless steel in the idea of the reactor pressure vessel, so that it will be the cladding, structural cladding materials. On the other hand, that if you have fuel pins and the fuel cladding for the fuel, those are not within the scope. Is that right, Sue?
That's exactly right, Sam.
Okay, thank you both for that. Moving on, for NM2, will the effects of radiation damage on creep and creep fatigue be considered important?
It's considered to be important in the following sense that a lot of the structural materials that we're looking at, sometimes that in the secondary, they might not see irradiation dose. For those components that are closer to the core, like reactor vessel, we'll see some fluence. So yes, irradiation can cause a sort of irradiation creep, and it could sort of interact with this sort of cyclic loading. But I would sort of look at the order of magnitude. Is that is the first thing first is that we don't have a really understanding of sort of the high temperature cycling and stress effect in terms of this. So if I can do everything all at once, yes. But if not, then we'll address the high temperature and the sort of the stress part. Since that the irradiation dose of our structural materials are not very high.
Thank you again. For NM2, is 3D printed, I should say, are 3D printed structural alloys relevant?
I think that we probably more in the NM3 sort of sub area. So we are looking at essentially what the sort of the raw product forms or sort of the more traditional fabrication route to support near-term deployment. And so probably that I will defer to Mei Mei in terms of the additive.
Yes, so NM3, it's advanced manufacturing technology, but certainly also interested in the material that made by advanced manufacturing technology, including the environmental effect in reactors. Yes.
Okay, thank you. And we had a clarification question come in with regards to the fuel cladding topic that you just spoke about earlier. And just to clarify one more time, the question says, fuel cladding materials are not considered structural for this topic. Is that correct?
I would say that fuel cladding is not considered to be part of NM2.
Okay, thank you, Sam. I'm trying to find, okay. For NM2, is fatigue of chromium cladding and silicon carbide CMC relevant?
Silicon carbide CMC is not. So in our slides to set what are the material, what are the topics that is considered to be out of scope for NM2 so for composites is out of scope. There are other places that to look at it. We essentially are looking at metallic components for structural applications like vessels, like piping, like that type of structural components in a high temperature reactors.
Okay, thank you. And this question is geared towards both NM1 and NM2. Are specific material fabrication approaches relevant?
For NM2, we consider that to be the traditional fabrication process, whether you make forgings, you make plates, you make pipes, or you make tubings or fittings using any sorts of malpractices and fabrications. So we look at it as all raw product forms. So we are not investing to develop those fabrication processes. Is that all of those fabrication processes are considered to be sort of available fabrication process for structural applications. So we are, NM2 is focusing on the materials aspects to look at sort of the creep damage mechanisms, fatigue damage mechanisms, and their interaction.
Okay,
For
and
NM, sorry, I also want to provide some input for the NM1 subtopic area. So for the NM1 area, I think the focus is not any particular material fabrication technique, because we are looking into the environmental assisted fatigue damage mechanism for materials that are currently of use in existing LWR fleet. And if you look at the type of materials Sue has mentioned, carbon alloy steel and austenitic stainless steels, you would find the right manufacturing process, probably the traditional ones like wrought alloys, casting, etc. And then you would look into how these materials are the environmental assisted fatigue applied to them, and how your studies can understand better that damage mechanism.
okay, it looks like we have a couple more questions for NM2 before moving on. The next one is if joining techniques of relevant structural materials are relevant to NM2.
Well, I would say that a weld is part of a structural component, so therefore that the underlying fatigue and quick fatigue mechanisms for a weldment, we would have interest in that. So for base metal and weldment, so for the understanding of the underlying damage mechanisms are also, we need to close those knowledge gaps and take advantage of those understanding through this type of work, so that we can be more efficient in terms of qualifying materials rather than by brute force mechanical property testing.
Okay. Are coatings considered composite materials and therefore not relevant to the NM2 work scope?
Well, coating in the general sense, like cladding and coating, they are not really, I don't consider that to be composites, but the coating by itself, that if it's make of considered to be some sort of metal instead of ceramics. Ceramics is out with the metal. We would like to understand the sort of what are the sort of the same type of failure mechanisms, but that our basic emphasis is more on the bulk structural materials, how you make a piping valves and those type of things, that I would say that coating will be lower in the order of priority, even though that one can sort of consider that to be part of a vessel if you put some coating to perform some other sort of functional requirement in terms of environmental, like corrosion. But we really want to sort of look at the chunk of about structural materials, how we can improve our understanding and leverage that so that we can qualify more structural materials for nuclear, for the fission reactor applications.
I will add that coatings and claddings could be included under the other category, so NM5, since those are of interest in general to the NE mission for advanced reactors that have particularly corrosive environments.
Okay, thank you for your answers to that. The next question is if high entropy metallic structural materials would be relevant to either and or NM1 and or NM2.
No, they would be outside the scope for those two topics. However, they are of interest in general to the NE mission for future materials. So I would look at the other category for high entropy alloys.
Thank you. We have a set of questions focused on NM3 now. The first of those is if you could please give us an example on the application of machine learning and artificial intelligence for NM3.
Well, certainly machine learning and artificial intelligence is a very important role in the area of developing manufacturing technology and also support the manufacturing process. So there are lots of applications, that can take advantage of the machine learning, artificial intelligence. So any innovative ideas are welcome for this subtopic area.
You, Mamie.
Yes.
Another question for NM3. Would a proposal on high throughput characterization techniques, so something along the lines of the development and its application to fundamentally understand the deformation mechanisms of advanced manufactured materials, would that be an idea that's relevant to NM3?
NM3 does include the emerging capability that developed that can help manufacturing technology development. So if the proposal can demonstrate how this high throughput testing technique can help the mature development or qualification of manufacturing technology, that's certainly of interest.
Okay. Next question. Are laser-based additive manufacturing technologies relevant to NM3?
So NM3 is about advanced manufacturing technology. Advanced manufacturing technology refer to the technology that has not been broadly used in nuclear space. So if the manufacturing technology can have a broad application in nuclear industry, that is of interest.
Hey. Would advanced approaches for metal heat treatment be relevant to NM3?
NM3 does cover the processing technique. So if there's a innovative technology development that can help the processing technology, that is of interest.
Okay. Does NM3 need to be focused on structural materials only?
No, this is advanced manufacturing technology that actually not limited to any particular structural component or cladding. So there's no requirement on that.
Okay. Would transformative processing and fabrication approaches for both light water reactors and advanced reactors be relevant to NM3?
Yes.
Okay. Advanced fabrication methods for cladding materials be relevant to NM3?
The answer is yes.
Wonderful. Is advanced manufacturing of silicon carbide CMC cladding relevant to NM3? And I may have asked that question earlier.
Yeah, we don't have a specific requirement on particular material or particular structure. So yes, so the interest is on advanced manufacturing technology for nuclear energy applications.
Amy, now we'll move into some questions specifically routed for NM4. Can you elaborate on what is meant by sorbent crosscut technology?
I don't know if John Vienna is on the call or not.
Kimberly, he wasn't on earlier.
Well, he was not going to be available until 4 o'clock.
Okay.
And I am emailing him now.
Okay, we can move on to some other questions.
Okay.
Yeah, there's several more for NM4, so we can come back to that one shortly. Do proposals need to address capture of both noble gases and iodine species, including organic species?
Repeat the question, please. I'm sorry.
Yeah, it's for NM4 once again. Do
Yes.
proposals to NM4, do they need to address capture of both noble gases and iodine species, including organic species?
No, no. It could be either for iodine or for krypton for noble gases.
Okay,
One or the other is not necessarily combined, but one or the other in a specific proposal request.
okay, thank you, Kimberly. In NM4, would sorbents using other metals be open for consideration?
Okay, John said he couldn't get in using the software. I'm sorry. I'm I'm sorry. I'm reading. John is trying to get on using this. He can't get on the call using the software. I'm not sure what that means.
Okay, Julie is looking into this, and
Okay.
we will find out if we can just send him a direct number that he can call in,
Okay.
possibly.
Perfect. Perfect.
Yeah.
Okay.
And while we're doing that, one moment, Stephen Kung, we will unmute you. Okay, Stephen, you are unmuted.
Yeah, can you
Okay.
hear me?
We can hear you. Hi, Stephen.
Yeah, good. Thank you. I think to add on what Kim said for the previous question, we prefer to have a sorbent to can catch all, but we understand it may not be possible. But our goal is to simplify the capture process. Of course, some sorbent material already can capture both iodine and noble gas, but their performance currently are low here. So in this case, we prefer to have a simplified sorbent that can capture all gases material. But again, Kimberly said, if we can separate that, that's fine with us, if we can demonstrate that.
Thank you, Stephen. Kimberly, Julie is still working on getting John in. So I will move into some questions for NM5 while she's doing that. So for NM5, can one propose development of advanced alloys, including design, high temperature mechanical, corrosion, and radiation damage resistance characterization for advanced reactors?
Yes, that would be part of the scope. I would encourage you in your proposal to ensure that you discuss why your ideas are better than what we have now, what the current state of the art is, and how it can be improved, and particularly what reactor type you'd be looking to advance the state of the art for materials development for.
Okay, thank you. Another question for NM5, which is the other advanced nuclear material topic area, is
I'm sorry, you broke up at the start.
Yes. Nope, I think we've got the NM5 question covered. So
Okay.
we do have some questions. Yes, Kimberly?
I'm sorry. John is on. He's just on the phone. He said he couldn't get the software to work. So I don't know if you could put him through.
Yes,
Just by the phone.
we will certainly try.
Okay.
John, if you can hear me, you should be able to hit the pound button and you can begin speaking. Okay, John, if you have done that, we are not able to hear you.
Yeah, Kimberly, I'm here. Maybe I can help. What was the question?
Hey, Stephen, the question for NM4 that was asked that we were trying to pull John in for is whether you can elaborate on what is meant by sorbent crosscut technology.
Oh, I think this the crosscut technology basically means we can offer the sorbent material for both aqueous process and the salt process. So in this case, we call it cross-cutting. So, but in specifically case, in any case, if you focus on iodine capture, if you, that should cover both aqueous or salt, that will be perfect. But if you want to separate them, that's okay as well.
Thank you, Stephen. Now we have a question that came in for NM2. So moving back to NM2 work scope, is coolant environmental effect a relevant topic for creep fatigue work in this work scope?
To the extent that it affects the fatigue damage mechanisms and the creep damage mechanisms and their interaction.
Okay, thank you, Sam. This follows a question that was asked earlier in NM3. And since advanced manufacturing technology of cladding materials may be relevant to both NM3 and FL3, both work scopes, are there any insights one of you can provide about guiding us to submit to the right topic area?
I don't know if we have anyone from the other topical area, but in terms of NM3, we are focusing on advanced manufacturing technology, not specific to any particular application or structure. So that's the focus of NM3.
We'll see if someone who's here from the fuels group would like to speak to that. Ken is here. Okay. So I know we just opened the mic for Ken Keller if he'd like to comment. One piece I will say on these types of topics is if there is a cross-cutting aspect, it's really up to the applicant to decide where the focus of the project is. If it's on the additive manufacturing technique, for example, maybe that has more applicability here. If it's much more focused on the fuels, where the advanced manufacturing technology or technique is a secondary factor, then maybe it's better in the fuels area. So I'll leave it to that. And Ken, if you have any additional comments, please feel free to comment.
Can you repeat the specific question? I faded a little because I was a bit of a passive listener there.
Yeah, sorry to put you on the spot, Ken.
No worries, no worries.
The question is, because advanced manufacturing technology of cladding materials could be of interest or relevant to two work scopes, NM3 and also FL3, the asker was inquiring about any insights that you can provide to guide them to the right work scope.
Well, one thing we presented yesterday is that any fuel concept has to have manufacturability and economics involved. So it's one thing to use additive manufacturing to make a very specialized, say, unique bracket in the reactor, some special shape. That's worth investing in. But cladding in general, we have boring a bunch of boring tubes, and it's a lot of tubes, it's a lot of material, and a lot of throughput, especially in once-through reactors. So if you're going to address cladding manufacture, it better have a high production rate and have the possibility of economical production. Otherwise, things like the normal tubing extrusion type processes and pildering, things like that. beat it out. So that's the only consideration I'd say. It's one thing to do a specialized part in the reactor. It's a very different thing to do large volumes of fuel cladding. I hope that addresses the question.
Thank you so much for being available for that question, Ken. Now there's two more questions here that I believe are more general. They don't appear to be focused on a specific work scope, but to topic area 7 in general. One of those questions is whether rock salt is among one of the materials that may be relevant to these work scopes.
I'm sorry, I heard rock salt, but then you faded out.
Oh no, I am sorry for the problems here. The question is whether rock salt would be considered relevant, a relevant material for these work scopes.
Those would not be of interest for in this particular topic.
Okay, thank you. And then the last question that we have here, are waste form materials for cesium and strontium relevant to these work scopes in topic area 7?
Kim, that's probably a better one for you.
I'm sorry, what was the question? I'm sorry.
Yes, the question is if waste form materials for cesium and strontium are relevant to the topic area 7.
For this particular subtopic, we're strictly looking at krypton and iodine.
Right, but under the other
can you hear me?
category, would it be something?
Yes, is that John?
Hello, hello? Can you hear me?
Yes,
Hi,
we can hear you.
Hi, John.
Sorry, I had technical complications. So I'm back on. So for cesium and strontium, they would fit under the general waste form topic, but they would be relatively low priority compared to the waste form for iodine.
Okay, thank you.
This is Stephen. I can add on some on this one, cesium and strontium waste issue here. Of course, this is of interest to our general fuel cycle topic or area. As John said, it may not be a high priority, but you are welcome to submit those kind of topics. If you, worst, you can go to the other topical area.
Thank you very much for that clarification, Stephen. John, while we can hear you, there were two questions that were asked, and they were focused on work scope NM4. Stephen provided us with an answer, but I wanted you to have a chance to share your thoughts if you would like, if you had anything more to add. The first of those questions is if you can elaborate on what is meant by sorbent crosscut technology in NM4.
So the term sorbent crosscut technology is a little hard to understand, but what we're basically looking for is sorbents that could capture either iodine or krypton 85, krypton chemically, I guess. And we don't expect there's likely to be a single sorbent that could capture both, but we may be surprised. Somebody might have something new. So individual sorbents for krypton and for iodine would be really our biggest interest there.
Thank you, John. We appreciate you coming online and sharing that perspective. And I think that was record number of questions for these work scopes. And that wraps up the last of the questions. And I will turn it over to Drew. He will be providing some concluding remarks. Thank you all.
All right, as we're getting things set up, I'd like to thank everyone for attending over the last 3 days, these work scope webinar sessions. I'd also like to thank Anna Podgorny, Julie Jacobson, and Tyler Newitt, who have been our production team this week here at the integration office. Their efforts both before this webinar and this week have been amazing. So with that, I want to remind everyone of a few things. First, the webinar resources, recordings, and a transcribed question and answer will be available before the FOAs are released. Typically, they're released beforehand as soon as we can get items prepped. The FOAs that we discussed on Tuesday we plan to release those by the end of August, and if that timeline changes, we will communicate with you, and associated anticipated deadlines will move to accommodate that type of whatever that release date may be. If you have additional questions, please submit those to nup@inl.gov. We'll direct those questions to the appropriate federal point of contact or technical point of contact as needed. And finally, as a reminder, we're planning additional engagement opportunities, and we will continue to communicate with all of you about those opportunities as they are finalized. So please stay tuned over the next few weeks as we continue to advertise those opportunities. Like I said before, thank you for attending. I hope you found the information provided as helpful, and please do keep in touch with questions as the funding opportunities are announced. With that, we'll call this wrapped up. Thank you.